For nearly half a century humanity has operated under a single unspoken rule of astronomy which dictated that if you truly wanted to see the raw and unfiltered majesty of the cosmos you had to leave the planet behind because the thick and turbulent blanket of Earth's atmosphere acted like a frosted window pane that blurred the ancient light of distant galaxies. We poured billions of dollars into orbital titans like the Hubble Space Telescope and eventually the James Webb Space Telescope, believing that the ground was a place for heavy iron and glass but the heavens were the only place for true clarity. However, that long-standing paradigm has just been shattered by a machine that breathes the same air we do yet possesses a vision so terrifyingly sharp and expansive that it has forced the global scientific community to stop and recalibrate their understanding of what is possible. Deep within the rugged and desolate peaks of the Chilean Andes, where the air is so dry it cracks the skin and the silence is heavy with the weight of geological time, a new eye has opened, and it is unlike anything our species has ever constructed before. The Vera C. Rubin Observatory has officially achieved its first light, and the images it returned from its very first night of operation are not merely beautiful or technically impressive but are fundamentally unsettling because they reveal a universe that is far more crowded and far more violent and far more alive than we ever dared to imagine. While traditional telescopes are like peering through a straw to see a single distant bird, the Rubin Observatory is like opening a massive cathedral door to witness 1,000 storms raging at once across a vast and endless ocean. What makes this moment so historic and so nerve-wracking for astronomers is the sheer scale of the data being harvested, because for the first time we are not just looking at the universe but we are recording it in high definition in real time. The heart of this facility is a camera the size of a luxury SUV capable of capturing an astonishing 3.2 billion pixels in a single exposure, which is a resolution so dense that it would take hundreds of ultra-high-definition television screens tiled together just to display one single frame without losing detail. Imagine a camera lens so wide that a single snapshot can hold 40 full moons, and yet within that massive field of view the telescope maintains a level of precision that can detect the faint glimmer of a single star exploding in a galaxy millions of light-years away. This is the moment that generations of scientists have dreamed of, because it represents the transition from static astronomy, where we take a picture and study it for years, to cinematic astronomy, where we watch the universe unfold like a grand and chaotic motion picture. In its first 10 hours of testing, this machine found more asteroids than the rest of humanity managed to find in several weeks of coordinated global effort, which serves as a chilling reminder of how much has been hiding in the darkness right over our heads. The initial images have sent a shockwave through the scientific world because they contain secrets that were previously invisible to our most advanced sensors, including merging galaxies that look like cosmic smoke and newborn stars screaming into existence within clouds of gas that span trillions of miles. We are diving deep into what the Vera Rubin Telescope has just seen and exploring why these first glimpses into the deep sky have left even the most cynical researchers in a state of genuine awe. Before these images were released, the observatory was already a legend in the making, perched atop Cerro Pachón in one of the darkest and clearest spots on the entire surface of the Earth, where the light pollution is non-existent and the stars look like heavy diamonds hanging in a void of velvet. It was designed to be a survey telescope, which means its primary mission is not to focus on one single object for weeks at a time but to scan the entire visible sky every few nights over and over again for a full decade. This constant repetition creates a time-lapse movie of the cosmos, allowing us to see the flickers and the pulses and the collisions that happen in the blink of an eye. The engineering required to achieve this is nothing short of a miracle of modern physics, because it utilizes a unique three-mirror design that provides a field of view and a level of sharpness that no other ground-based system can match. Most telescopes use two mirrors, which limits their perspective, but the Simony Survey Telescope at the heart of the Rubin facility uses its massive 8.4-meter primary mirror to funnel light into a precision optics system that defies the traditional limitations of atmospheric distortion. This is not just a tool for looking at the stars but a machine built to map the very fabric of space and time itself by capturing ultraviolet and visible and near-infrared light with a precision that makes the vacuum of space feel within our reach. We are standing at the edge of a new era where the mysteries of dark matter and dark energy and the origins of our own solar system are no longer hidden by the limitations of our technology but are being laid bare by a camera that never blinks and a telescope that refuses to look away. This is the story of how a machine on a mountaintop in Chile changed everything we thought we knew about the scale of the heavens, and why the first night of the Vera Rubin Observatory will be remembered as the night the universe finally started talking back to us in a language of pure and overwhelming data. When the primary shutters of the Vera C. Rubin Observatory finally slid open in June 2025, the scientific community held its collective breath because while the engineering team knew the machine was capable of greatness, they were not prepared for the sheer density of information that would flood into their servers within the first few seconds of exposure. This initial test run resulted in a massive digital mosaic that astronomers quickly and affectionately nicknamed the Cosmic Treasure Chest because it represents a 25-square-degree portrait of the southern Virgo cluster, which is the closest large collection of galaxies to our own Milky Way galaxy. To understand the scale of this achievement, you have to realize that this single image was stitched together from over 1,000 separate exposures, and yet it maintains a seamless and breathtaking clarity that allows you to zoom in from a wide view of the cluster down to the individual spiral arms of a single distant galaxy millions of light-years away. In this one image alone there are millions of stars and tens of thousands of galaxies, each one acting as a possible home to billions of planets and perhaps even civilizations that we have never dreamed of, because the depth of the field is so profound that even the smallest red dots in the background represent entire island universes. The image captures spiral galaxies stretching their arms lazily across the void of space like glowing whirlpools of fire, while nearby merging galaxies twist together in a violent dance that looks like cosmic smoke frozen in a moment of total destruction. What makes this mosaic truly unsettling for the researchers is the realization that this overwhelming richness of data actually represents only 0.05% of what the Rubin Observatory will eventually detect over the course of its 10-year mission. This first masterpiece was merely a trailer for a decade-long film that the universe is about to broadcast through the lenses of this Chilean giant. Because the observatory is on track to reveal over 20 billion galaxies, which is more galaxies than there are people on the surface of the Earth. As the astronomers began to explore the layers of the treasure chest, they found more than just aesthetic beauty. They found the unfiltered evidence of cosmic evolution happening right before their eyes in a way that ground-based telescopes had never captured with such immense scale. They saw delicate filaments of gas and dark matter connecting distant clusters in a web-like structure that defines the very architecture of the universe, and they saw the faint reddish glow of ancient galaxies that have been traveling through the darkness since the beginning of time. This first mosaic has reshaped our understanding of what a first light image can be, because it proved that we no longer have to choose between seeing the big picture and seeing the fine details, since the Rubin Observatory provides both at the exact same time. If the first mosaic demonstrated the raw power of the telescope, then the subsequent release of the wide-field mosaic of the Lagoon Nebula proved that a ground-based facility could rival the most famous space observatories in terms of depth and complexity. The Lagoon Nebula is a star-forming region located about 5,200 light-years away from us, and while we have seen beautiful zoomed-in portraits of its core from the Hubble Space Telescope, those images were always like looking at a single room in a massive mansion. The Rubin Observatory, however, showed us the entire estate by providing a panorama where the nebula itself, despite spanning 55 light-years across, only occupies a small fraction of the total frame. Surrounding the glowing gas of the nebula are countless points of light, including open clusters like Messier 21 and the densely packed globular cluster NGC 6544, which sits thousands of light-years further back in the distance. This layering of objects at wildly different scales and distances within a single sharp image is the direct consequence of the staggering field of view that this telescope possesses, because while Hubble sees a tiny fraction of the Moon's surface in one shot, the Rubin Observatory sees an area equivalent to 40 full moons at once. This means that for the first time in human history we are seeing the Lagoon Nebula not as an isolated and pretty object in the sky, but as a connected piece of a much larger and much more chaotic cosmic landscape. We can see the neighborhood filled with the birth and death of stars and the motion of gas clouds being pushed by the radiation of newborn giants, all within a single data set that remains sharp and intricate from corner to corner. This is the true revolution of the Rubin project, because it turns the sky into a living map where the relationships between objects become visible and the context of the universe begins to make sense. The scientists realized as they scrolled through these first images that they were looking at a neighborhood of chaos and motion where everything is influencing everything else, and the static portraits of the past are now being replaced by a dynamic view of a universe that never stops changing. The treasure chest is only the beginning, because every 3 nights the telescope will go back and do it all over again, checking for what has moved and what has faded and what has suddenly exploded in the darkness. This transition from a single snapshot to a continuous monitoring of the heavens is what makes the Rubin Observatory a true cosmic machine, because it is not just taking pictures, it is extracting the hidden structure of the universe frame by frame and delivering it to our screens with a speed that humanity has never experienced before. The Vera C. Rubin Observatory was never intended to be a mere factory for beautiful photographs, because its true soul lies in its function as a revolutionary cosmic alarm system and a sentinel for the safety of our own planet. While the public marvels at the swirling colors of distant nebulae, the scientists behind the project are focused on the terrifyingly efficient way the telescope can track the moving shadows of the solar system. In its very first 10 hours of operation, the observatory identified over 2,000 new asteroids, including several near-Earth objects that had previously escaped detection by every other telescope on the surface of the globe. To put this into a perspective that highlights the sheer scale of this machine, the combined efforts of all other observatories worldwide typically detect around 20,000 asteroids in an entire year, but the Rubin Observatory is poised to discover millions in its first few years of service alone. This makes it arguably the single most important tool humanity has ever constructed for planetary defense, because it provides us with a high-definition radar for the darkness of our own backyard. By scanning the entire sky every 3 nights, it can catch the faint movement of a space rock against the backdrop of static stars long before it becomes a threat, allowing us to track its trajectory with a precision that was once relegated to the realm of science fiction. However, its role as a guardian of Earth is only one of its 4 major pillars, because once you look past the asteroids and the nearby planets, the telescope begins to probe the most profound mysteries of the physical world, specifically the invisible forces of dark matter and dark energy. We know that everything we can see in the universe, from the glowing stars to the massive galaxies, makes up only about 5% of the total mass and energy that exists, while the rest is a ghostly and unseen scaffolding that dictates how the cosmos behaves. The Rubin Observatory will search for the fingerprints of these invisible giants by mapping how billions of galaxies cluster together and move across the vast stretches of space and time. By observing the subtle distortions in the light of distant galaxies caused by the gravity of dark matter, a phenomenon known as weak gravitational lensing, the telescope will allow us to create a 3-dimensional map of the invisible universe. It is effectively a machine designed to see the unseeable by watching how the visible world reacts to the hidden forces around it. This is why the data pipeline is so critical, because every night the facility produces 20 terabytes of information that must be analyzed in real time to catch transient events like supernovae and gamma-ray bursts as they ignite. This capability transforms astronomical research from a passive study of the past into an active monitoring of the present, because the Rubin Observatory acts like a security camera for the entire southern sky. If a star suddenly pulses with an irregular rhythm, or if a supernova flares into existence in a galaxy halfway across the universe, the telescope will record it and broadcast the coordinates to the global scientific community within 60 seconds of detection. This rapid scanning cycle ensures that we no longer miss the brief and violent transformations that shape the evolution of galaxies, because we are finally watching the sky with a cadence that matches the speed of the universe itself. Behind this wall of discoveries lies a digital behemoth of 500 petabytes of data, which is a library of information so vast that it will take generations of researchers and advanced artificial intelligence systems to fully unpack and understand. We are not just building a map of where things are, but a record of when things happen, which allows us to trace the history of the universe through the lens of constant change. The implications for our understanding of the Milky Way are equally transformative, because the telescope is also tasked with tracing the ancient architecture of our own galactic home. By identifying and tracking over 100,000 RR Lyrae stars, ancient pulsating objects that act as standard candles for measuring distance, the observatory will create a skeletal map of the outer reaches of our galaxy. These stars often float in the distant galactic halo where the light is faint and the distances are immense, but the deep imaging capabilities of the Rubin Observatory turn these difficult targets into routine observations. This mapping process will reveal the hidden tidal streams of stars left behind from past collisions between the Milky Way and smaller dwarf galaxies, allowing us to read the history of galactic cannibalism that built the world we live in today. The observatory is effectively a time machine and a cartographer and a guardian, all wrapped into one precision-engineered package of glass and silicon. As it continues its decade-long vigil, it will rewrite the rules of astrophysics by showing us that the universe is not a static graveyard of cold stars but a living and breathing organism that is constantly evolving and expanding and revealing new secrets to those who have the courage to look at the big picture. To understand why the images from the Vera Rubin Observatory have sent such a profound shock through the scientific world, you have to appreciate the sheer mechanical defiance required to take crystal-clear pictures from the bottom of a turbulent ocean of air. For decades, ground-based telescopes have been treated as second-class citizens compared to space telescopes like Hubble because our atmosphere is a chaotic mess of temperature shifts and humidity and dust that distorts incoming starlight into a blurry soup. This atmospheric cage is exactly why we spent billions of dollars launching sensitive instruments into the vacuum of orbit, but the Rubin Observatory has successfully challenged this limitation by combining an elite location with a camera that feels like it was stolen from a future century. Built on the jagged cliffs of Cerro Pachón in the Chilean Atacama Desert, the observatory sits within one of the most stable air columns on the entire planet, where rainfall is practically a myth and the sky remains dark and transparent for the vast majority of the year. This pristine environment allows the telescope's massive three-mirror optical system to funnel light into the largest digital camera ever constructed by human hands, which is a 3-ton masterpiece of engineering that stretches nearly 3 meters in length. This camera is not just a larger version of what you have in your smartphone, but is a precision instrument housing 189 individual sensors that are cooled to cryogenic temperatures to eliminate electronic noise and ensure that every single photon of ancient light is recorded with absolute fidelity. The sheer resolution of 3.2 billion pixels means that the telescope can resolve details that are effectively invisible to any other ground-based system, allowing it to rival and in some cases even surpass the depth of space-based observatories across a much wider field of view. But the true magic of the Rubin project isn't just in the glass and the silicon, but in the invisible digital infrastructure that acts as the observatory's brain, because this facility produces a staggering 20 terabytes of data every single night. This is an amount of information so colossal that it would cause traditional research networks to collapse under the weight, which necessitated the construction of a dedicated 100 gigabit per second fiber optic highway that beams data directly from the mountaintop in Chile to processing centers in the United States. This pipeline is the first of its kind because it is designed to act in real time by calibrating images and correcting atmospheric distortions and identifying moving objects before a human being even has a chance to look at the screen. What the Rubin Observatory is creating is not a collection of static photographs but a dynamic and living digital universe that updates its own internal model every 3 days as the telescope completes a full scan of the southern sky. Imagine a world where the star charts are no longer frozen in time but are instead a breathing representation of the heavens that reacts to changes faster than astronomers can even think. If a supernova flares into existence or an interstellar object streaks through our solar system, the system catches it and integrates that new data into a constantly growing map of the cosmos. This transition into the era of big data astronomy means that we are no longer searching for needles in haystacks by hand but instead using massive automated algorithms to sort through trillions of measurements to find the anomalies that will redefine our laws of physics. The camera uses a robotic arm system to swap filters at high speed, allowing it to transition between ultraviolet and visible and near-infrared light in a matter of seconds, which gives us a multi-dimensional view of the chemical signatures and thermal clues hidden within the starlight. This technological leap has effectively democratized the universe because through tools like the Sky Viewer application, the immense data sets that were once restricted to elite researchers are now being made accessible to anyone with an internet connection. We are entering a period where a student in a classroom or a hobbyist on their couch could be the first person to spot a rare stellar pulse or a hidden comet simply by scrolling through the high-resolution mosaics provided by the Rubin facility. The observatory is a shift in perspective that signals the end of an era where we look at the universe as a series of isolated objects and the beginning of an era where we see it as a connected and sprawling landscape of birth and death and motion. By converting the night sky into an ever-expanding database, the Rubin Observatory has ensured that the discoveries of the next decade will happen at a pace that is completely unprecedented in human history. Every exposure is a layer of a much larger tapestry that reveals the hidden structure of space and time frame by frame, and as the petabytes of data continue to pile up, we are finding that the universe is much more complex and much more beautiful and much more accessible than we ever imagined it could be.